So let me start by recalling that this is being filmed and that the slides are going to be made available online afterwards, because I will only be showing some of the slides for a short while. So this talk is about general to specific modeling with user-specified estimators and models. So this is a feature or utility we provide in an R package called Gets, which is on the CRAN. And this is a package I have developed together with Felix Prittis at University of Victoria and James Reed at the University of Reading. So what is general to specific modeling? Let me try to explain that in terms of linear regression, but let me also hasten to add that Gets modeling is not limited to linear regression. In fact, that's one of the main purposes or main motivations behind the idea of providing user-specified Gets modeling. So a key challenge when you model, so you have a set of regressors you would like to select among. You have your favorite left-hand side variable, sales or whatever, and you would like to find, ideally, the x's that matter, that have an influence on what you would like to model. And also you would like to exclude the regressors that don't matter, the ones that are not relevant. So this is model selection. And what Gets modeling do is that it combines well-known ingredients in a very well thought through way. The ingredients are backwards elimination along multiple paths, t-tests of the coefficients, multiple hypothesis tests of the coefficients, goodness of fit measures, and diagnostics tests. And the final model is such that it's a parsimonious model that contains the relevant variables with probability 1 as the sample size goes to infinity, and on average, and this is a really useful part, a proportion of irrelevant variables equal to the regressor significance level alpha. So the way you control the error is by basically tuning the regressor significance level. And asymptotically, you can control that in a very predictable manner. And I will come back to that later when I say more about Gets modeling. Okay, so I should basically provide the caveat that these are asymptotic properties. When you work in finite samples in practice, you will, of course, not necessarily always be able to basically achieve these properties, but an extensive amount of simulations over 20 years, more or less, suggests that it holds very well, even in fairly small samples in a range of contexts. So Gets modeling provides a comprehensive, systematic, and cumulative approach to modeling that is ideally suited for conditional forecasting and scenario analysis more generally. And the origin of Gets modeling is basically with econometrics, modeling of economic data. Okay, so how does Gets modeling perform compared with other algorithms? And the answer to that question is very well. Here are some simulation results compared with some other well-known algorithms. I'm not going to present these results in detail. I'm just going to refer to our Journal of Statistical Software paper, which is cited at the bottom of this page here. So this is freely available on the net. I've also cited some other references on Gets modeling. You can see here that Gets modeling is not new. It has been around for some time. And over time, it has been refined, and various aspects of it has been studied, and there's quite a lot of literature on it. So why user-specified Gets modeling? Well, if coded from scratch, user-specified implementation of Gets modeling puts a large programming burden on the user. So what we and in addition, Gets modeling is computationally intensive. I guess that's the main drawback with it, since many models must be estimated and checked and or diagnosed. So we provide a flexible and fairly computationally efficient framework in R for the implementation of gets modeling with user-specified estimators and models. And almost needless to say in this context, one of the motivation for that is that you can facilitate the use of all the estimators and models that are potentially out there in the R universe. It should be said, though, that because of the simplicity with which you can use R to communicate with other languages, you can actually, in principle, take your estimator model in another language and just provide a small interface, so to speak, a coded interface in R to call your estimated in an external language. The main function for user-specified gets modeling is gets fun. And to provide a preview of one of the examples, which I will be relating to, is a situation where you fit a model with a well-known LM estimator. So you obtain, you retrieve an LM object. And if you create a so-called gets.lm function and you apply that to my model, you will be able to actually do gets modeling straightforwardly to your well-known LM object. And to relate this back to John Fox's presentation earlier, so I'm not sure how the LM object actually stores your splines inside it, but if they are stored as regressors, you might actually be able to, no?
Well, there would be a model matrix stored in the linear model object.
Mm-hmm. Yeah. So it could be, depending also how the splines are generated, it could be that this actually could work straight out of the box. That's a potential usefulness in a sense to relate back to your talk. Okay, so this is the outline. Gets modeling more detail, user-specified gets. I won't be able to provide all the examples in detail, so to basically already now say a little bit about what we do. So basically we provide example code of how to do OLS faster using the matrix package. We also provide an example of how to basically do automated gets modeling on the regressor matrix in an ARMA model with regressors. So this is with the ARIMA function. And we also basically provide the code for how you can make a gets method for the LM class of models. So let me recall that gets modeling basically contains 4 ingredients: backwards elimination along multiple paths, confusion to significant testing, both individual and joint, fit criteria, and diagnostics testing. And gets modeling proceeds in 3 steps, or it can be described as proceeding in 3 steps. Formulate a starting model, a general unrestricted model, and optionally they should pass a chosen diagnostics test, then do backwards elimination of the insignificant regressors along multiple paths, while at each regressor removal testing for joint significance and checking their diagnostics. This increases power and also adjusts, in a sense, the p-values for multiple testing to a certain extent. Finally, since you do backwards elimination along multiple paths, you might end up with several terminal models. So the idea is that at the end, you choose among the terminal models with a fit criterion, for example, an information criterion. And now favored criterion is the swatch information criterion because it favors parsimony. We start with a lot of variables, or we tend to start with a lot of variables in gets modeling, and that's why, in a sense, we favor the swatch information criterion, at least as a default, but that can be changed by the user. So let me take you through a very simple example. We start with a model with 3 regressors. A little bit unusually, I have put the 2-sided p-values in the square brackets beneath the estimates. And if we choose a 5% significance level, then we can delete along 2 paths. We can either start by deleting x1, because we see that the p-value is larger than 5%, which means that our next model is one without the x1, and we see there that one of the p-values is higher than 5% on x3, so we delete that one as well, which gives us this model, which only contains x2. This is our final model, because there's no more regressors that are significant at 5%. So this is the terminal model of path 1. Okay, we go back to the starting model. Instead of deleting x1, we now start by deleting x3. That gives us a new model, but now both of the remaining regresses are significant 5%, so this is the terminal model, which means that we have two different terminal models. The way we choose among them is with a fit criterion, and as I indicated, our favored or our default fit criterion is the Schwartz information criterion, which means that one of them would be preferred. I haven't explicitly showed that we actually, in addition, or by default at least, one does parsimonious and comparison testing, which means multiple coefficient tests, and also a check of the diagnostics at each removal. Okay, so as I indicated at the start, one of the really interesting properties with the GETS modeling is that first, as your sample size goes to infinity, you will retain all the relevant regresses. But in addition, on average, you will retain alpha times k irrelevant regresses, where alpha is the chosen significance level for the t-test. So what does that mean? Suppose you start with a model with 100 irrelevant regresses. Then you will, on average, retain alpha times 100. So if you choose a significance level of 10% times 100 irrelevant regresses, then we will, on average, retain 10 irrelevant regresses. So if you, as a user, think that that's too much, you reduce your significance level to 5%, for example. Then you will, on average, retain at the max 5 irrelevant regresses, and so on. With a significance level of 1%, you will on average retain 1 irrelevant regressor, and so on. Okay, so in order to implement user-specified gets, you do that with the gets function in the gets package. And the main arguments are y, left-hand side variable, x, which is the regressor matrix, and user estimator. This is a list containing the name of the user-specified estimator model and further arguments to be passed on to the estimator. So to give you an idea of how it looks like with the default, which is a function called OLS, which we have made for our package. So this is a fairly fast OLS estimator. So this is how it looks like. To give you a quick example, so here we have some code. At the bottom here, you can see the code for executing gets modeling applied to this example here. We have 40 observations, 20 regresses. All of them do not matter by construction. This is the output. We start by searching across 18 paths because that's 18 insignificant in the starting model. So first we delete regressor number 1 in path 1, then regressor number 15, and so on. Takes about 1 second. 308 estimations are done during that second. This is path 18, and these are the two distinct terminal models. Selecting between them, it states that the best terminal model is number 1, which contains 3 regresses. The default is 5% regressive significance level, which means that in this example, you should, on average, retain 1 irrelevant regressor. Here we retain 3, which is slightly more, but this is because it's a Monte Carlo for this specific seed of the regresses. Okay, so in constructing your user-specified gets estimator, you should construct a function of this form. Y must be a vector, X is a matrix, and the estimator must return a list with 6 entries. The coefficients, the coefficient covariance matrix, the degrees of freedom used for the t-statistics, a log likelihood, or alternatively another value for the goodness of fit criterion that is used, the number of observations, and the number of coefficients estimated. And it must also be capable of returning a null regressor. So it must also be capable of handling null regressor matrices. This is because it might actually delete all the regresses. we have you can specify the diagnostics via the user diagnostics argument and also the goodness of fit criterion via the goodness of fit facilities. Okay, so I mentioned we have 3 examples, so I'm running out of time. I won't be able to provide the examples in details. You can look at the code on the slides. So these will be made available online. And yeah, so it more or less looks like this. Okay, so let me quickly provide the outlook. So our software is continuously developed, maintained, and improved. We are currently trying to fully, so we do have something called indicator saturation in this package. And we are basically, the idea is to also facilitate user-specified indicator saturation. And we'll also improving, so we currently have parallel computing for the ISAT part, but not for the reduced get part, and we're trying to basically enable that fully for the moment. That's basically what we're currently working on. So thank you a lot, and here are some websites that you might consult if you are interested.
Thank you very much.
What is the, my question is, what is the size of the NP matrix for your input? So what is the number of lines for respective to the number of columns?
You talking about the regressor matrix? Or what are you talking about?
Well, if you, in your data set, can you have a rectangular matrix, a square matrix?
If I can have what?
Your input, in your input, how many lines for how many columns? If you have, say, 12 columns, 12 inputs, 12 hits, how many lines, what is the minimum number of lines?
Okay, so is this related to whether we can have more variables and observations? So we can do that in GETS modeling. We haven't enabled that feature yet in the user-specified part. And the way it is, so obviously you can't fit all less, or at least not according to the standard method, so if you have more variables than observations. So the way this is enabled in GETS, and which we plan to enable it in the user-specified part, is by organizing the full number of regressors into blocks. So that means that the challenge is actually how you combine the blocks so that you conceptually enable more variables and observations and still retain asymptotic properties, which you are aiming at. I think that's an answer to your question.
And let's assume that you have at least the number of lines is larger than the number of columns.
Yeah.
Is it just n plus 1, or is it p plus 1, or is it p plus 10?
Well, I guess you need, technically, for inversion to go through, I think you can have k equal to n, but that's useless in practice. I mean, you need, because the degrees of freedom is then 0, so you need a certain amount of degrees of freedom. You have to remember that the properties, strictly speaking, are asymptotics, which means that the degrees of freedom actually goes to infinity. So you need, so for whether, to what extent that actually works for small degrees of freedom, it depends on the data, depends on the model, depends on the estimator, and so on. So, but in practice, I mean, computationally, you can have n equal to k, but that's useless in practice because you won't get any informative information from that sort of estimation.